want to hear anything again, I know I talked kind of fast. So when you're graphing a quadratic equation in standard form, you want to identify the a, b, and c. A is the coefficient of the x squared variable, so we're looking right here. B is the coefficient of your x variable, and then c is your constant. The degree of any quadratic equation is 2. The shape is a parabola. This one opens up because our a value is positive, and therefore because it opens up, it has a minimum. The vertex is a minimum. To find the axis of symmetry, we use the formula x equals negative b over 2a. Our b was 5, so the opposite of b is negative 5, and 2 times 1 is 2. So we have our axis of symmetry, x equals negative 5 halves. To find the vertex, you take your x value and substitute it into the equation for x and solve for y. And we found that was negative 20.25. For the x-intercepts, if you can factor, you can find them easily. In this case, we factored our quadratic equation to x, the quantity x minus 2 times the quantity x plus 7. So because they're in the asylum, the actual x-intercepts are the opposite, 2, 0, and negative 7, 0. To find the y-intercept, substitute 0 for x and solve for y. When it's in standard form, as this equation was, the x squared term will become 0, the x term will become 0, so your y-intercept is your c value. And then we plotted all of the information on the graph, the vertex, the two x-intercepts, the y-intercept, and then we use the axis of symmetry to reflect the y-intercept across the line to get another point so we could graph our parabola more accurately. Second example was a parabola in factored form. So I kind of worked backwards on this one. I started at where am I? I started at D, finding the x-intercepts. So this was in factored form. We had the x minus 4, so the first x-intercept was positive 4. And then we had x plus 2, so the second one was negative 2, again the asylum. And then I worked backwards to find the axis of symmetry, part B. You take the average of your two x-intercepts, so that work was right here. 4 plus negative 2 over 2 gave us 1. So that was the axis of symmetry for part B, as well as the x-coordinate for the vertex in part C. So once we know the x-coordinate of the vertex, we substitute that into the function, so that work is right here. Y equals the opposite of 1 minus 4, quantity 1 minus 4 times the quantity 1 plus 2. So that's how we got our y value of 9 for the vertex. Degree, shape, same as the first example, opens down because we had that negative sign outside the parentheses, scrolling back up right here, so that's why the parabola opened down. And because it opened down, we had a maximum value. Y-intercept, we substituted 0 for x into the equation and solved and got 8. So then we plotted our vertex, our intercepts, and then again use that axis of symmetry to reflect the y-intercept. Next type of quadratic is in vertex form. So remember the asylum, this negative h, when you're looking at the vertex, turns into a positive. Whatever's outside the asylum is normal, so that was a positive case. So looking at our first example, y equals negative 3 times the quantity x minus 5 squared plus 2. Inside the asylum we have the negative 5, so the x-coordinate is positive. Outside we have a positive 2, it's normal, so it stays positive. For our second example, we have a positive 4 inside the asylum, so that's really a negative 4. Negative 7 outside the asylum, that's normal, stays negative. So it's just a little practice identifying the vertex. The next one we'll take a look at how to graph it. So there's two methods for graphing with vertex form. For both methods, the first thing that you need to do is identify the vertex. So again, right here, we've got positive 5 inside the asylum, so our x-coordinate is negative 5. Negative 1 outside the asylum, so that's normal, so our vertex is negative 5, negative 1. The axis of symmetry is x equals the x-coordinate of your vertex, x equals negative 5 on this one. And then find the y-intercept. So remember that's substituting 0 for x and solving for y. So when we do that, we get 5 squared is 25, minus 1 is 24. So we have a y-intercept of 24, axis of symmetry x equals -5, and our vertex is -5, -1. One other thing we need to do before we graph is identify if it opens up or down. In this case, we have a positive, or we have nothing outside those parentheses, which is a +1, so our graph opens up. With this y-intercept of 24, I'm going to have to do a big scale on here. So let's see. I'm going to do a scale of 4. So right here would be 0, 24, again using a scale of 4. And then our vertex, -5, -1, using a scale of 4, we're going to go left like 1 1/4, and then down just 1/4. And then using the axis of symmetry, I'm going to reflect that y-intercept across the axis of symmetry over to here. Sorry, calibration's off just a little bit. And then make sure you get that U shape again when you're graphing the quadratic. So there's method 1, using the vertex and the axis of symmetry to graph with a vertex form. Method 2 is using a t-table. So you find the vertex. We're still looking right here. Inside the asylum is negative, so that means it's a +3. Outside the asylum is negative, so we have a -4. And then you can do a t-table around the vertex. So I put the vertex in the center of my t-table, and you want to find 2 values on either side. So I would use 2 and 1, and I would use 4 and 5. And then you can plot these values, your ordered pairs from your t-table, to get your parabola. So once you have your x values figured out, you substitute those in to solve for y. This one, again, noticing here, and this isn't as big a deal with the t-table because you'll get the ordered pairs to plot, but notice that it opens up, so make sure that your graph is consistent with what the equation says. So I'm going to substitute 2 in for x, and we got -1 squared is 1, times 2 is 2, minus 4 is -2. I'm going to substitute 1 in here. 1 minus 3 is -2, squared is 4, times 2 is 8, minus 4 is 4. And then to save a little bit of time on the other side, we also get -2 and +4. So I'm going to plot my points here. I've got 1, 4, and I'm using the scale that's on the graph. I've got 2, -2. I've got 3, -4. 4, -2. And 5, 4. And then again, just making sure that you've got the U shape versus the V shape for the absolute value. All right, so that's the end of the quadratic graphing review. Next, we're going to take a look at graphing lines and absolute value. So to graph a line, there's several different ways to do that. This is in standard form, and what I notice is the coefficient for x and y are both factors of 6. So I would graph this first one using x and y intercepts. So I'll substitute 0 for y to solve for my x-intercept. 6 divided by 2 is 3. So I have the ordered pair 3, 0. Substituting 0 for x and solving for y, I get a y-intercept of 6. So I plot those 2 ordered pairs, 3, 0. I'm going to go as a scale of 1 since I have to fit 6 on here. So here's my 3, 0, and then 0, 6. And then make your line. Ooh. Try and make it a little bit straighter. Make sure you put arrows on the end as well. And then taking a look at the absolute value. Remember, this is the V function. And you can find the vertex for your absolute value similar to the way that we find the vertex for the quadratic equation. So this looks like a +5, so we have a -5. Outside the asylum is -4. Notice there's no vertical scale change on the outside, and there's no horizontal scale change on the inside. So what that means is that the slope of our absolute value is 1. So I'm going to plot my vertex. I'm going to go by a scale of 1. I'm not going to use the scale on this one as well. And then you've got your slope in either direction is either 1 or -1. So you just go corner to corner. And again, make sure on this one, oops, I missed a corner on that side, sorry. Make sure that you do have that pointed V to differentiate the absolute value between the quadratic. Inequalities on a number line. So this is where we have one variable, and we're just plotting our answer on a single number line. So we solve our inequality. I'm going to start on the right-hand side with distribution. So I've got -2x minus 6 and 7x minus 15. So adding 2x to both sides, adding 15 to both sides, and dividing both sides by 9. Remember, if you multiply or divide an inequality by a negative, you have to flip the symbol. So that's why I chose on that second step to add the 2x to both sides so that my coefficient for the x term was positive, and then I wouldn't have to mess with flipping the inequality. So because we have x is less than 1, that is an open circle, 1 is not part of our solution, and less than shades left. Alright, so on our second one, this is a compound inequality, it's an OR. That means whatever works for either inequality, we just shade everything on the number line. So we solve each inequality, add 2, divide by 5. On the second one, we're going to add 6, divide by 2. And these are both less than, so when I graph these, the first one, x is less than 1, and then the second one, x is less than 5, ends up shading into that open circle from the first one. So 1 is a solution because it works for the second inequality. With the absolute value inequalities, if you remember that cheesy saying that I gave you, when you're starting with greater, then it's an OR compound inequality when you set it up. So we start with just dropping the absolute values, and there's our first inequality. Or we keep what's inside the absolute values the same, the 2x minus 7. We're making that 14 negative. So what happens is we have to flip our inequality. So we have 2x minus 7 is greater than 14, or 2x minus 7 is less than -14. So when you think about the values that you're substituting into the absolute value, if 2x minus 7 is greater than 14, you'd have numbers like 15, 16, 17. And when you take the absolute value, that's greater than 14. If it's less than -14, you'd have values like -15, -16, -17. And once you take the absolute value, it becomes positive, which is greater than 14. So that's why we're splitting it up this way. So we solve each inequality, add 7 to both sides, and divide by 2. And if you want to put that on the number line, convert that to a mixed number or decimal, that might be helpful. So then we take a look at the second one, again adding 7 to both sides and dividing by 2. Now because what we divided by was positive, we don't flip the symbol on that one. So again, to convert that to a mixed number to graph, I would do that. I'm not sure why this one is missing its number line. But we have 10.5 and -3.5. I'll just plot those generically. Open circles on both of these because we have the less than or the greater than. And the OR again means shade everything. So x is greater than 10.5, so that's to the right, or x is less than -3.5. So remember, with the absolute value compound inequalities, the ORs should always be shaded to the outside, and that is one way of telling whether or not you did that right. If you have an and, it should always be shaded to the middle. Again, those are just for the absolute value inequalities, not for all of them. I ran over onto the other side, so I'm going to erase a little bit of this work so that I can do our second inequality. So again, this one, our cheesy saying, actually, let me back up. We've got a coefficient on this one. So before we split this up into two inequalities, we have to cancel that outside coefficient. So I'm going to divide both sides by 2 first. That's an absolute value. Now we're going to think about our cheesy saying. We have a less than, so it becomes an and. So we've got 5x plus 3 is less than 6. So the first one, all you do is drop those absolute values. The second one, again, what's in the absolute value stays the same. The inequality flips because we're making this 6 a negative. So again, thinking about this, if 5x plus 3 is less than 6, we have values like 5, 4, 3, which is less than, and I'm looking at this one here, which is less than 6. If 5x plus 3 is greater than negative 6, that gives us values like negative 5, negative 4, negative 3, and the absolute value of those will be less than 6. Solving each equation, subtract 3 from both sides, divide by 5. Same process over here, but the subtracting by 3 gives us a little bit different value. Divided by 5. And this is an and, so we're going to shade everything. So we've got the 3/5, which would be about here, and the negative 9/5, which is just shy of negative 2. If x is less than 3/5, that would shade this way. Greater than negative 9/5 would shade this way. So we know we did that right because they're meeting in the middle. We only shade where they're both true, so they only overlap in between the two answers. Graphing systems. So we have a chance to see another way of graphing lines. The blue line, I notice that 2 is not a factor of negative 5. So instead of using fractions to graph this one, I'm going to solve for y. So I'm going to subtract that 2x from both sides and use slope-intercept form. So we've got negative 5 is our intercept, and I think I can use the scale that's on here. And negative 2 is our slope, which means we would either fall 2 and go right 1, but I don't have room for that, so I'm going to go up 2, left 1. And sorry that this is off just a little bit. And we get our line that way. All right, for the red line, I would do intercepts on this one again because the coefficients are factors of 2. So my y-intercept, substituting 0 for x, would be 1. And substituting 0 for y would give me an x-intercept of 2. Which gives me 2, 0. So plotting these points, I've got 0, 1, and 2, 0 for my intercepts. So what I'm noticing for these is not what I should be noticing. They meet off the graph, so I probably should have used a scale of. Okay, so I thought I paused the recording, apparently I didn't, sorry. So what we can do is we can look at this one again in class and I'll use a more appropriate scale, sorry about that. They should meet somewhere. Graphing systems of inequalities. So what I'm noticing about this first inequality is that it's a horizontal or a vertical line because I only have a y value. So I think about where does my y value equal 4? And that's a horizontal line. I think we use a scale of 1 this time just to make sure we get this all fitting on the graph. And this should be dotted because it is just less than. So just less than or just greater than, we should have dotted lines. For my second one, very similar, y is greater than negative 3. So that one will go here and we'll have a dotted line as well. And for my green equation, I've got it in slope-intercept form. So my y-intercept is negative 2. And my slope is 3, so I'm going to rise 3 and run 1. Run to the right 1. And I like to plot a lot of points when I'm doing systems so that I can see exactly where they intersect. And this one is dotted as well. So for the shading, remember with systems of inequalities, there's a solution area that's shaded. Y is less than 4. Line. Y is greater than negative 3 would be shaded above the red line. And it's hard to tell with a line that has a slope other than 1 or 0 which side to shade on. So one thing to do is to check a point. So in this case we could check the origin, 0, 0. Substitute that into the inequality, 0 greater than 3, times 0 minus 2, and ask ourselves, is it true? Is 0 greater than negative 2? And the answer is yes. So we would shade towards the origin from the green line. So where I notice the blue, red, and green arrows all pointing towards each other is in this section. So that's where I would end up shading. And that is done. So the rest of the review will be done in class.